Welcome to this tutorial on modulation, in particular amplitude modulation. Now, I am firmly of the belief that when it comes to explaining engineering terms, it's often best to avoid the maths as part of the explanation and the teaching and concentrate on the visual. So that's what I'm going to be doing here. I think that the maths is best used to support and to prove the explanation, but not to deliver it. So, I've created this Excel spreadsheet which shows amplitude modulation in a visual manner. And if we look at it, the first thing to note here is that down the bottom here we have a conventional amplitude modulation waveform that you've often seen in the past, as the amplitude of the waveform changes over time, which conveys the data. We're going to be coming back to this and we're going to be looking at it quite a lot. Above here I have a mathematical expression for an AM waveform, and you'll see that it's made up of three terms here: first term, second term, and a third term, and I'll come back to that as well. Here is the AM waveform shown in the frequency domain. We'll come back and address that. Up here is the modulating wave and the carrier wave shown in the time domain. Up here is a calculation on the modulation index, and then over here is our input parameters. The first thing to really recognize is that a waveform, or the first thing to understand, is that a waveform is basically a sine wave. We see that here. This basic expression for a waveform. This is the magnitude of the wave, its peak value, it's a sine wave, this is its frequency, and any phase shift. Now, all of these examples I'm having a phase shift of 0, just to make life easy. Down here we've got our carrier wave. Now this is often represented, the magnitude of the carrier wave is shown as an A. Again, it's a sine wave, the carrier frequency here, and our phase shift. The modulating frequency, or usually often thought of as our data, the magnitude of the modulating frequency is got a magnitude of m. Again, it's the same expression, but the frequency of the modulating wave is often presented as FM as opposed to FC for the carrier. Now, over here in my spreadsheet, we can put some numbers into this. So at the moment, our carrier frequency has got a magnitude of 10 volts. It's a sine wave. It's at 10 hertz. Our modulating waveform has got a magnitude of 5. Again, it's a sine wave, and it's at 1 hertz. Now, when it comes to AM modulation, one of the things that often students are asked to calculate is what's called the modulation index. And the modulation index is simply a ratio of the carrier wave to the modulating wave. A ratio here of 10 and 5. Gives us a modulation index of 0.5. If I was to change this to 10 and 2, we would get a modulation index of 0.2. If I was to change the carrier to a magnitude of 5, this ratio here, 2 to 5, is 0.4. So that's all the modulation index is. We'll just put these back to what they were. There. Now, down here we have our AM waveform, and as I said, this is the mathematical expression, and this expression here explains what's going on in here in the time domain. We can see that in this expression there are three sine waves. Here's the first one, which is the carrier wave. The magnitude of the carrier wave, it's a sine wave, it's at the frequency of the carrier waveform. That's pretty much it. Here we see it here. Okay, here's our sine wave. The second thing that's in here is what's called the upper sideband, and this is it here. It's a sine wave, and it's got the carrier frequency. It's got the upper sideband frequency is the carrier wave plus the modulation wave, FC plus FM. 10 plus 1 is 11. We can see it here. 10 plus 1. There it is there. There's our upper sideband. The second expression here is another sine wave, and it is at the carrier minus FM, 10 minus 1 in this case, 9. Now if we were to change these to, say, I don't know, we'll call that 3, that will obviously go to 13 and 7. There it is there, 13 and 7. Now, how big these sidebands are is defined by this expression here. The magnitude of the sideband amplitude, is the modulation index times the magnitude of the carrier divided by 2. 0.5 times 10 over 2 is 2.5 volts peak, which is 1.8 RMS. We can see that here. When we go down here to it in the time domain, we can see that, let's try and get some nice good values that make it nice and easy to see. There we are. With a magnitude on the carrier of 10 and a magnitude on the modulating wave of 5, the peak value is 15. 10 plus 5. 10 minus 5. We can see that all the way through here. And if we follow this thing through here, we can see that there's a sine wave on here. And this here, the frequency of this is our modulating wave. We can see this here. It's exactly the same. Likewise on the bottom. So the waveform is nice and symmetrical, and we can see this. If I was to double the frequency here, we would double this of the modulating wave and double this. So let's do that. We could make, for example, the modulating wave the same magnitude as the carrier wave. The ratio of 10 to 10 is 1, so that would give us a modulation index of 1. There it is there. What's interesting to note is that we can go into a state of overmodulation, where we can make the modulation index greater, the magnitude of the modulating frequency greater than the carrier. And this creates something called overmodulation. We can see that here, where our waveform would come and transition through the zero crossing. We made it a little bit more noticeable, and we might increase the frequencies to make it a little bit more transparent. Here it is here. This is what happens when we end up with an overmodulated wave, where the modulating frequency magnitude is greater than the carrier, and we end up with a modulation index of greater than 1. And that's the key definition of overmodulation, a modulation index of greater than 1. Thanks for watching.